Am I audible? Okay. Good morning, everybody. I'm thrilled to be here. Thank you, Udayji, Dr. Vats, Deepali ji. It is a great privilege for me to be here today, a great honor as well, and a very inspiring moment for me. I'm very impressed by the initiatives over here. Man making, character building, nation building. This is your mission. This is amazing. And this comes from none other than Swamiji himself, from Swami Vivekananda. He has been an inspiration to generations. Generations before me, my generations, and generations after me. Swamiji, his character was so unique. A lot of people have said many things about him. And I can quote anybody. But I've chosen to quote Netaji Subhash Chandra Bose on Swami Vivekananda. He says, reckless in his sacrifice, unceasing in his activity, boundless in his love, profound and versatile in his wisdom, exuberant in his emotions, merciless in his attacks, but yet simple as a child. He was a rare personality in this world of ours. He goes on to say, Swamiji was a full-blooded masculine personality. And I've chosen this quotation with a purpose. He was a fighter to the core of his being. He was consequently a worshipper of Shakti and gave a practical interpretation to the Vedanta for the upliftment of his countrymen. Now, I chose to begin to talk with this because I'm talking to future citizens of this country. The message here is your health, fitness, be very strong and be prepared to attack what is wrong. I think there is a tremendous message in this, and all of you are very fortunate to be here at the Vivekananda Institute, which can really shape your life in a very big way. It's a great privilege. So I would like to congratulate all of you for joining the right institute. I think this is a wonderful atmosphere over here. Professional studies. What kind of professions come to your mind? Teacher, scientist, medical professional. Your chairman began his career as a physician. Engineers, computer specialists, nurse, electrician, carpenter, street cleaner, toilet. You can think of a number of professions. Anything that can give you an opportunity to become a man making, character building. You can lose anything, somebody can take away your shirt, but nobody can take away your character. Man making, character building, and nation building. All of these professions, they contribute to build the nation. The country cannot exist without any of these. So I feel very proud that I am at this institute which has for its goal these ideals. So health and fitness is very important in this. I'm sure you have opportunities for many adventure sports, usual traditional sports, outdoor sports, indoor sports. if you already are into, if not, get into some. I would like to mention that I got into adventure sports at a fairly late age in my life. Somebody had told me that I was your age. I did not have that. But at a late age, I got into trekking and mountaineering. I set up the first mountaineering club at IIT Madras. Took several treks to the Himalayas, including Ladakh, which you were mentioning, Zanskar Valley and other places we have been to. I got jump hurdles, very treks. And these really changed my life because it gave me confidence. It taught me that yes, there are things I have never done, but which I can do now. That was a huge lesson for me. It impacted me in many things, which is why I continue to learn after my retirement also. I had to confess that I got into computing after my retirement from IIT Madras. IIT Madras has a retirement age of 65, so I retired from there. I'm not more than 70. I have been using quantum mechanics all my life, but it's not the same as getting into quantum computing. So quantum mechanics certainly lays the foundation for quantum computing, but quantum computing is a very specialized area, and I was able to get from IIT Madras during the years I was at IIT. It's very privileged because, Swami Vivekananda, when I was your age, I read his books, the Karma Yoga, Bhakti Yoga, Jnana Yoga and Raja Yoga. I was most influenced by two of these books. One is Karma Yoga and the other is Jnana Yoga. I did not connect easily enough to the other two. And I was reminded of what I had read in Balagangadhar Tilak. He has written a commentary on the Bhagavad Gita, and he says that this is something that you must learn when you're young. A lot of people in our society learn these things after they have retired and nothing worthwhile to do. What it says in the preface, in the introduction to the Gita Rahasya, is that you must learn it when you are young, because then you can use it in your life, not when most of your life is gone. So that's the right time, and you can learn many things from many different sources. One thing that appeals to me in this institute is the focus on interdisciplinary studies, because that's from what little I know about studies, is that there is strong encouragement to professional studies in interdisciplinary areas. So this is very important, and I would like to toss a few ideas to pursue over here. If you look at it's like, let me suggest a sequence of numbers, like 525, 125. You know what I'm doing? 0, 1, 1, 2, 3, 5, 8, 30. Now, well before Fibonacci, this was actually known to mathematicians in India. It was known to other mathematicians, including, I think, Pingala. It was known earlier. Now, the importance of the sequence, some people call it as the Hemachandra sequence now, not as the Fibonacci sequence. is it leads you to fractals. Are you all familiar with fractals? If you look at a cauliflower, okay, and you see pieces inside the cauliflower, they look like the whole of the cauliflower. If you take smaller parts of it, they look like the earlier part, and you can keep going deeper and deeper in the structure of these. So fractals are objects of this kind. And what is interesting is that when you talk about dimension space, if you look at this, say this is one dimension, take the other side, it is, take another one, third dimension. Fractals are objects which have fractional dimension. That is the reason they are called as fractals. I would like to quote, what is his name? Gerd Binnig. He is a Nobel laureate. He got the Nobel Prize for inventing the scanning tunneling microscope. Binnig said that the study of fractals, which belongs to the entire discipline of the theory of chaos, he predicted this, I think around 1989 or 1990, that fractals and the theory of chaos would make as much a revolution in science, engineering, and technology as quantum mechanics and relativity has done in the previous century. So one of my recommendations over here would be to initiate study of the theory of chaos, because it is bound to make a difference. It is making a difference in all branches of engineering, medical practices. The ECG signal that you get sometimes shows fractal behavior. The cells, subparts, you get into fractal structures. So it is having applications in all branches of human knowledge. So that would be an important recommendation I would like to make to this school. One way of doing it is for students to launch studies, because there is nothing like experiential learning. So take up projects, do new things which has fractal applications. You have a rich heritage in this country in music. Means people used to come to India to learn mathematics, astronomy, and even medicine, Ayurveda, but they continue to come to India to learn classical music. Take up a project in which you can compose new music using fractals. Like if you take up some raga, like Malkaus or something, or any other raga, select a set of notes and see what you can do with those notes by repetitive applications. You can compose new music, write a code for that. You need to be very proficient in coding in tomorrow's world. Projects in which you can find new applications of fractals. You could end up inventing new mathematics. Let me tell you the story of a young this was 400 years ago, thereabout. 17th century. He was about your age. I think most of you must be close to 20. There are plus minus few years. This student was 21 years old. He was interested in watching the planets, how they move. And he asked himself, can I predict the position of this planet tomorrow? Where will it be tomorrow? I see it here today, it's going to move, where will it be tomorrow? So he's looking at a certain angle, and tomorrow it will be right? Where it will be tomorrow. You need delta t in the limit delta t going to 0. You need d theta by dt. You need rate at which that. And he was looking at it when there was no calculus. The idea of a limit did not exist. The limit of a function, that okay, what happens to the value of a function as the parameter gets to a certain point. Calculus, which did not exist. This was Isaac Newton. But then, if you go deeper, you will find some of them probably knew even before Newton. Because otherwise, could they come up with the Panchang so accurately? This is a matter of investigation. I have friends who are to talk about it, so I will not get. These are fascinating areas in which you can contribute to knowledge in a very big way. New mathematics is invented one of the fundamentals is to get simultaneous and accurate value of position. This is known as the Heisenberg's principle of uncertainty. Why is it important? If you look at any object, whether there is a water bottle over here, and I keep it here, and I ask you to tell me what is the position of this bottle and what is the momentum of this bottle. The reason these two properties are important is because if you look at any object, you can talk about a number of physical properties. You can talk about the color of the object, you can talk about the shape of the object, you can talk about the mass of the object. Okay? Many properties can be thought about. But when you want to talk specifically about mechanical properties of the object, then you're talking about motion and dynamics. And the color doesn't matter, because whether this bottle contains water or milk, if I drop it, it will fall at the same acceleration due to gravity, which is 9.8 meters per second or whatever. So these are the mechanical properties, and only two fundamental mechanical properties will determine all the mechanical properties. These properties are position and moment. So you recognize, you appreciate the importance of position and momentum. Now comes the question, how will you get this information? Who gives you this information? What is the position of this bottle now? To be able to talk about the position of this bottle at this point of time, I need to set a coordinate frame of reference and say that, okay, this is my x-axis, this is my y-axis, this is my z-axis, and then tell you what is the xyz coordinates of this. Then I have to carry out some measurement and determine the rate at which it is moving, get the velocity, and with that I can tell you what the momentum is. Now, without these experiments, there is no way I can talk about position and momentum. And this is the important thing about these two physical quantities. Can I get the position of this object if there was no light in this? I possibly could, the way blind people do. I can stretch my hand, go this way, and then say the bottle is here. So I could still tell you, and if I had a good judgment of space, I could tell you that it is at, 1.5 meter from where I am. But I need to do some experiment. Either I have to scatter light, either I have to bounce light from it, or touch it. Or maybe if it has got an odor and I have a strong sense of nose, then I could say that okay, it is in this direction because I get the smell from this side and not from that. But you need a sensor. And without that probe, it is impossible to tell where the position is. And we agreed that position and momentum are extremely important to do any mechanical study. So let's consider one of these probes. Light has to bounce off this bottle. And how many of you have seen comets? Find comets, okay? You can see some comets. There are good telescopes available in Delhi. You can see some comets. Please go and do that. I'm sure you have read about the comets and you know that the comets have a tail. Does anybody know why it has a tail? Anybody? Loudly. If you have an answer, stand up and say it loudly. Yes.
So that would be because of high velocity they are traveling with, and due to friction it causes a bit of tail to form a...
Unfortunately, that's not the correct answer because there is nothing to have friction with. Its comet is traveling mostly in empty space. So that's not the reason. The reason is that sunlight falls on it. And the sunlight pushes the dust on the comet. And the light scattered from that dust is what appears like a tail to us. How do you know that this is the correct answer? Because the tail is always directed away from the sun. Okay, when the here the tail is directed in that direction. When it is here, it will be in that direction. Okay? The point I'm trying to make is that when light falls, there is a transfer of momentum. And if I want to see this bottle by shining light on it, that light will push it. And the position of that object will no longer be what I had intended to measure. And it is impossible to measure position and momentum simultaneously and accurately. Do you understand the fundamentals of Heisenberg's principle of certainty? It's impossible to do that. And if it is impossible to do that, then how would you study physics? Because you need the position and momentum. Without that, you cannot study mechanical properties. So quit physics or find a method to do physics which is not based on simultaneous information of position and momentum. You have to invent new way of doing physics. This new way is quantum theory. It is a mathematical framework which allows you to do physics even if you cannot get simultaneous information of position and momentum. In classical physics, which is the mechanics developed by Newton, or beginning earlier than Newton, beginning with Galileo, Newton, Lagrange, Hamilton, and so on. So you can do physics using this alternative theory. It is now 100 years old. Heisenberg's paper and Schrodinger's paper are about 100 years old. And it was a revolutionary idea because it begins with the tenet that you cannot represent the state of a system by position and momentum. How do you represent it as an alternative? You represent it by a vector Hilbert space. Now, what nonsense is this? I mean, you're talking about physical objects, and now you're talking about an abstract mathematical space, which has some analogy to the space that we live in. It is also one-dimensional space. It has got its own structure. It has got its own mathematical set of laws. And it seems so abstract, which has nothing to do with this bottle. And now you're saying that the state of this bottle, the mechanical state of this bottle, is represented not by position and momentum, but by a vector in the Hilbert space. It is so mind-boggling. An out-of-the-box idea, which would seem like nonsense. It was revolutionary. And the fact that it worked, how did it work? You had to develop the Hilbert space. And Dirac says in his book, one of the founders of quantum theory, that you connect it to physical properties as you develop the algebra further, which means that you have to take a good course in quantum mechanics. Maybe you have to take 2 courses in quantum mechanics, or maybe 3 courses. But it is accessible to undergraduate education. And once you learn this, then you develop the algebra further and figure out that you can describe all the properties of this water bottle using mechanics. Nothing succeeds like success. The theory works. I can accept it, even if it's started out by appearing to be nonsense. It worked. It works not just for microscopic particles like electrons, protons, and so on. Sometimes you read books in which it is said that for macroscopic particles, for big objects, classical physics should be used, and for tiny subatomic particles, you must use quantum mechanics. This is a very misleading thing. Quantum mechanics is the correct theory. It works not only for tiny particles, but also for large objects. Not only does it work for large objects, it is not possible to explain everything about large objects without invoking quantum mechanics. So quantum mechanics is a very powerful theory, universal theory. It is applicable to everything, small and big. Whether you need it for big depends on the questions you're asking. If you just want to know a tiny bit about what is the trajectory of a cricket ball which has been hit by Virat Kohli when you see a sixer, and you want to predict how far it has gone, you can do these calculations using classical physics. But it doesn't mean that you cannot do it using quantum theory. The answer you get from classical physics is good enough for the purpose of listening to a commentary and appreciating the shot. But that doesn't mean that it is fully correct. It's not. You need quantum theory even to explain means I'm standing here, I'm not falling through the floor, and you can ask, why am I not falling? Because the floor is after all made up of atoms. Atom is mostly empty. There is a nucleus occupies just about a Fermi distance, 10 to the minus 13 centimeters. And then the electrons around it are at various distribution. But the atom is mostly empty, and through that empty space, am I not falling through the floor? Or why are you not falling through the chair on which you're sitting? The same question. Now this is not, we are not talking about tiny microscopic parts. We are talking about large objects. I think I'm too large already. So, if you want to explain this phenomenon, at some level you have to invoke quantum mechanics. So quantum mechanics is applicable for all small and large objects. I would like to come to quantum theory because I think one of the objectives of this meeting is to trigger a discussion on entering undergraduate programs in quantum entanglement, quantum computing, with futuristic applications. I have brought with me a paper, one of the most prestigious journals in science, as some of you may be knowing, is Nature. And this is an article from Nature, a very recent article. It was published on 16th November 23, just a few months ago. It is the rise of the quantum engineer. So let me share. I have got some copies which Udayji has got for me. So let me share this. Yeah, we have some more copies. If you can read it, it is a rise of the quantum engineer. And there are undergraduate programs which some universities have actually started, in which they have initiated a career in quantum engineering. Chaos theory is the first thing that I mentioned, which I think is very important, perhaps as important as quantum engineering is. But I would like to recommend engineering physics and also quantum engineering. Engineering physics is because technology benefits from engineering, and engineering requires fundamental science for its foundation. Engineering physics is a great program because that will teach sciences, mathematics, which is absolutely important, and then you can develop applications in engineering. So engineering physics is also a very exciting program for the future. Quantum engineering is another discipline. It is unstoppable. Talk about this expressing the state of this water bottle by a Hilbert space. It is a revolutionary idea. This is what people now call as the first quantum revolution. And the reason they do it, because there is a second one in progress. And let me tell you the difference between the first and the second quantum revolution. The first quantum revolution was to represent physical states of systems by a vector space and developing the mathematics to get physical properties out of it, which is quantum mechanics, which is quantum theory. Now this was revolutionary, but very fruitful, because what came out of it are things like semiconductors, lasers. All of these developments came out of this. But it had some questions. And these questions are hotly debated. Not by ordinary intellectuals, but by intellectual giants. And I'm referring to Niels Bohr and Albert Einstein. Now, there was a huge debate between Einstein and Bohr. Bohr had an intuitive idea of quantum theory as to why it works or how it works. I think he knew how it works. Nobody knew why it works. What people know now is that it works. They don't know how it works, or they don't know why it works. You're trying to describe nature. If he has a question, I'll be happy to answer. But it required a probabilistic description of nature, a fundamentally probabilistic description. It is coded in the words uncertainty principle, but it appears in many more exciting it has many exciting applications in quantum theory. So you need statistics. And let me ask, when is it that you need the idea of statistics? When do you need probability? Am I taking too much time? Yeah. You have to tell me how much time I have.
You have it.
Okay. Please just signal me. Yeah. So when your cricket captain goes for a toss and he spins a coin, and he will have the right to choose ball first if he calls out correct. What's the probability that he will get it right? What is it? Half? Because it's either heads or tails. Now, if he knows I don't have a coin, now I use UPI, so no currency in my pocket. But if I know where I keep the coin, and I know how much, with what force I'm tossing it, okay? I know where the torque is applied, how much torque is applied. I can predict how high it can go. I can predict where it will fall and whether it will fall on head or tail if it begins with the heads up. Can I not? Yeah? So it's completely deterministic. But you're now talking only about a probability of getting your answer right. And the reason is because you do not know. Dhoni is tossing this coin and he does not know how much torque is applied, he doesn't know what is the density of air, what is the humidity, what kind of... So these are the unknowns of the problem. But these are all local unknowns, they're there. If only this information was available to Dhoni, and if he put this calculation quickly in his mind, he would win every single toss. Do you agree with that? Yeah? He can do it. So the probability is not intrinsic in the process, but it is because of unknowns. These unknowns are called as hidden variables. You understand the term hidden variables? And these hidden variables are all local. They're right here. They are in where the torque is applied, what is the density of air, what is the humidity of air. These are the hidden variables. And Albert Einstein's view was that quantum theory requires uncertainty and probabilistic expression because of hidden variables. And if only these hidden variables are detected, there would be no need for the quantum principle of uncertainty, which is the Heisenberg principle of uncertainty. Whereas Niels Bohr said that no, there is something intrinsic about the laws of nature which requires quantum theory, which has nothing to do with hidden variables. Now imagine the debate between two intellectual giants. This was first in 1927 at Solvay conference. Almost anybody who was anybody in physics was there. There is a very famous picture. How many of you have seen the 1927 Solvay conference picture? Please Google it, get a copy of that picture. That is a fantastic picture. It has got the photographs of the most number of Nobel laureates in one picture. So Dirac was there, Schrödinger was there, who wasn't? The debate continued for many years, from 1927 to 1935. In 1935, Einstein wrote a paper in which he tried to show the fallacy in quantum theory. In fact, in one of the debates at the Solvay conference, Einstein brought up, he was a genius at inventing what are called as thought experiments. So Einstein suggested a thought experiment in which he would prove that the uncertainty or the probability in quantum theory is because of hidden variables. And Niels Bohr would tell him what was the missing in Einstein's argument to prove Einstein wrong. So Bohr took up this challenge and he always found a flaw in Einstein's argument. In fact, at one point of time, Bohr invoked the general theory of relativity, which Einstein had missed out, a theory which he had himself developed. A very fascinating story. Please go through it, and you might want to enact the Bohr-Einstein debates over here. Means how one of the students play Bohr and the other Einstein. It will be fantastic. So, 1935, Einstein wrote a paper to show fallacy in quantum theory. Bohr replied, showing the fallacy in Einstein's argument. But the debate continued. But it did not stop quantum mechanics from making tremendous advances. That is a period when semiconductors, lasers, everything came out. 1960s, when the lasers came out. And it took 30 years, I think 1964 or 65, that a young man, he was an accelerator physicist, but he felt that both Einstein and Bohr missed something. Because Einstein was arguing, Bohr was counter-arguing, but neither of them suggested a way out as to how to determine whether the probability in quantum theory is due to hidden variables or was it intrinsic to the laws of nature. There was no method which either of them suggested. So this was suggested by this young man, John Bell. And he came up with a logical scheme which finally results in a mathematical equation. You got a left-hand side and a right-hand side, and the left-hand side must be less than or equal to the right-hand side. That was the nature of the equation. This is called as Bell's inequality. So he said that, okay, if this inequality is satisfied, then there would be hidden variables. If it is not satisfied, there won't be hidden variables. So it was, a matter of, black and white. You have to make a choice. And these experiments were eventually performed, they were carried out, and that is the reason the 2022 Nobel Prize was given to Alan Aspect, Zeilinger, and Clauser for this. Now this has led to what we now call as the second revolution. This comes from suggestions in the early 1980s which were made by Richard Feynman, there were others, Benioff, David Deutsch, and so on. And they figured out how to use quantum entanglement to do computing. I'm sure all of you are doing computing, and your entire algorithm is based on the Boolean algebra. 0 or 1, right? It's either 0 or 1. And then you can develop logical gates. Okay, the AND gate, the NAND gate, and so on. And using these gates, you can build circuits and build your computers. So all this computing, even if you're using a semiconductor, which is a quantum device, is called as a classical computer, even if it is using a quantum device. The reason it is classical computer is because it is using classical logic, which is Boolean logic, which is either 0 or 1. Now, nature has a different way of expressing herself. We do not know what it is. We did not know what it is till we developed quantum theory. And this is really an amazing thing. I will like to, I have not brought any slides or pictures to show, but I will try to explain it in a very simple way. If I have a sheet here, and I make a hole here, and another hole on this side, and I pour sand from the top, what do you expect to gather at the bottom? You expect a heap below the first hole and another heap below the second hole, maybe some overlap and spread. But basically, you expect two heaps. When you perform these experiments carefully, what you see, and these are real experiments, I do not know if you have these experiments set up in your labs, but it can be very easily set up in an undergraduate lab using lasers. So I think, do you have the Young's double slit experiment here? You do? How many of you have done the Young's double slit experiment? Wonderful. So you know what you see at the bottom is not a single heap, but you see fringes. You see some place where there is a heap and another where there is none, and you see alternative heaps. And you can explain this result only by invoking quantum theory, because what quantum theory requires is the admission of probability that the particle could go either through slit 1 or slit 2, but both have to be taken together. You cannot rule out any one of these possibilities. How could you rule out any one possibility? You can just close one shutter. Another way of doing it is that you keep both the shutters open, but you shine light below the holes. And whether you see a flash from slit 1 or slit 2, you could tell from which slit it has gone. You can do these experiments. And the results are, I would say, typically ghostly. Common sense will not seem to explain. So I will remember our granddaughter once under a tree, and these pebbles were missing the next day. And she concluded that they must have been taken by a ghost or a witch or a vampire. That was her conclusion. And the results that you get from these two slits are really as if they have been engineered either by a ghost or a witch or a vampire. Because if you try to shine light under the slit and find out, then the fringes disappear. This is incredible. It doesn't make common sense, but then that's how it works. Which means that if you can no longer talk about a switch being either on or off, which is the basis of Boolean algebra. Okay, all your logic circuits, all your logic gates work on this simple thing, that you have a binary system, it is either 0 or 1. And what we are discovering now is that you have to admit a state which is a superposition of 0 and 1. It cannot exclude one or the other, and this now becomes a unit for doing calculations. So your unit of doing calculations is no longer a bit, which is either 0 or 1, but it is a superposition of 0 and 1, a little bit of 0 and a little bit of 1. And this superposition is now the quantum bit. What it leads to is entanglement, which is the fundamental basis for teleportation and for quantum computing. I think I will stop here by suggesting that these are important things to learn, because it will be impossible to implement cyber security without this. There are other applications like drug discovery. You're trying to find a drug like some vaccine which will be useful against the COVID virus. How would you do it? You begin with some chemicals, mix them, do some chemistry, come up with some drug. It may not work, then you try another. And you have to employ large number of scientists in very well funded, sophisticated labs, and then see how effective the drug will be. Alternative to that, as all of you can think about, is to simulate this. And you do this simulation, but think about doing this simulation using classical binary logic. So you will write a program and you will have an if-then-else statement. How many if-then-else statements would you need for this? In the IIT Madras lingo, we call it as hajar. Okay, it means very many. So it's like asking a question. From here, you have to go to the Qutub Minar. How will you get there? You can choose one way. Somebody else can choose another way. The person who chooses this way finds that there is a traffic jam over here. The person who then he has to come back, find another road. He finds that the road has broken down, the bridge has fallen, something, right? So he has to take decisions about going left or right many times. And you're talking about left or right, good or bad, right or wrong, it's 0 or 1. It's binary. And if you use this logic, the algorithm would be extremely difficult. Whereas, if you use the properties of nature, which tells you that the physical state is represented not by either 0 or 1, but by a superposition of 0 and 1. So your code will explore all the alternatives in the same run. Okay, what happens if you go left and what happens if you go right? What kind of situation will you land up with? All of these possibilities would be explored simultaneously, which is why doing calculations with quantum computers will be so effective. So you need it in all branches of human endeavor. And I'm sure some of you can make very important contributions to this field. Udayji talked about the quantum mission. Yes, there is huge funding and great opportunities, but I will also like to caution that it is not going to be easy to tap into this funding, because you need to demonstrate your capability to be able to use it. So you need to do some tiny projects, get into it, show some success, prove that support to your institution is justified. And that's not going to be very easy, it's challenging, but that's something for you to do. We can assist in whatever way we can. I'm in touch with some quantum computing new industries, and perhaps some of you can do internships with them and so on. So we can talk about it later. I'll be happy to take some questions. Thank you very much. Yeah, any question, you can ask about how long it takes for me to go to the airport from my home in Bangalore. Any question? Yes. Yeah, there is a question there.
Recently there has been some debate that quantum computers may not scale well, because the number of bits that are there, they are not able to make that number goes higher.
Please say that again, I missed it. Yes.
The number of bits on quantum computers, that currently they are not that high in industry. So what is the possibility that it doesn't scale at a
Well, the industry is going very rapidly, and people are building quantum computers with a large number. When you said bits, I'm sure you meant qubits, because the unit of quantum computation is a qubit and not a bit. Qubit is a superposition of 2 bits. So now people are already using, but this is a very challenging technology. About 1,000 qubits are being used. But it is very challenging, but there is a lot that you can do even with a fewer number of qubits. I would suggest that for your first problems, you just work with 2 or 3 and for yourself what you can do with that. The technology is growing very rapidly. It requires very sophisticated experiments, which is why these technologies are developed only where very large investment is possible. So Microsoft, Google, Honeywell, these are the industry giants which are into it. But I don't think that is a big problem for us. We have to be able to come up with logic gates, quantum gates, which will solve real problems. Yes, there was some question from here.
Sir, like you said that quantum mechanics or quantum theory is also being used to solve problems for macroscopic objects. So sir, my question is like, it has been said, the great theory of everything, basically the theory that solves problems of all scales can't be developed in physics. So why can't quantum physics or quantum theory be classified under that?
I'm not sure I understand your question. Can you elaborate?
Sir, in physics, there has been quite a debate that a single theory that defines every unit in nature or the space can't be developed. We need multiple theories to explain different phenomena. So as you said that even macroscopic and microscopic phenomena can be explained using quantum theory. So why isn't quantum theory yet classified under great theory of everything?
Well, it solves many problems, but not everything. Everything involves various different points of view and different considerations. So if you look at how physics developed in the last century, helping us making progress in this century, there are 2 major theories. We have been talking about, and it has its origins in the fact that the speed of light is finite. In vacuum, it is a constant no matter which observer measures it, which is really very strange. Because if you and I are walking relative to each other, and if we look at the speed of a car, you will have a different answer for the speed of the car than what I will. Because you have to make correction for our relative speeds. So what came out of this consideration is the theory of relativity, which is called as the special theory of relativity, but then it is a special case of what? It is a special case of the general theory of relativity, which involves gravitation also. Okay, that any 2 masses have got a certain attraction between them. It has not been possible yet to develop a theory, and that is your question, which reconciles both quantum mechanics and relativity. That's where the bottleneck is. And that has not been possible as yet. People are working on it. There are working on it. They have answers, they are speculative. And it's difficult to test them. It is difficult to say that the theory is correct. It is also equally difficult to say that the theory is wrong. And that's where the challenge is, but that's also where the opportunities are. But there is no theory of everything as yet. And I doubt if there will be one, at least for the next few decades.
Okay, sir.
Any other question? Yes?
Okay, good morning, sir. Actually, my question is related to quantum entanglement. I would like to first ask your definition. What do you mean by quantum entanglement?
Okay, very good question. I would have loved to talk more about it, but good that you have brought up this question.
So what is the question?
Yeah. What's your name? Yash? Yash is asking what is quantum entanglement. So let's go back. I will take some time to answer it. Yeah. Let's go back to this earlier discussion we had that you cannot know the position and momentum together. We reconcile with that. But now I suggest an experiment in which I have got a particle. It breaks up into two identical particles. So two particles are born out of this friction. One particle goes to the east and the other goes to the west. Okay. These are identical particles flying apart. It's like an electron and a positron coming out of the disappearance of a photon. Okay, or it can be a diatomic molecule which bursts. One atom goes to the east and the other goes to the west. And these are identical particles. If it is an oxygen molecule, O2, one atom of oxygen goes to the east and the other goes to the west. Both are absolutely identical. You are there, you measure the position of this particle. And your friend is on this side. He measures the momentum of this particle. And from the position that you have measured, you can tell that the other particle is as much away because both were born moving together, identical particles. They are going together. So you predict where the position would be. Your friend on this side has measured the momentum. Got it? And you could tell that from conservation of momentum, what would be the momentum of this particle? Can you get simultaneous information about these two particles, both position and momentum? Have you beaten the Heisenberg principle of uncertainty? It would look like that, right? As a matter of fact, this is one of the arguments which was brought up by Albert Einstein. This is called as the APR paradox. It's named after Einstein, Podolsky, and Rosen. APR paradox. And the paradox here is that you have proposed an experiment in which you can beat the Heisenberg principle of uncertainty. And if you still cannot beat it, as it turns out is possible due to measurement, then it can only be if these two particles are connected in some way, which is entanglement. And if you invoke this entanglement, you can account for the fact that you cannot beat the uncertainty principle. So this is entanglement. What is interesting about it is that this argument that we just discussed has nothing to do with how far you are away from this spot or how far your friend away is this spot. You can be where you are. You can be in another hall behind that wall. You can be in another town beyond Delhi, or you can be in some other galaxy. And irrespective of where you are, no matter how far these two observers are from each other, this entanglement would stay. And you might wonder, how does the information pass from one observer to the other if nothing can move faster than the speed of light? Now this is entanglement. It has nothing to do with information crossing, because information is not passing from here to there or from there to here. What has happened is that our perception of here and there has to be corrected. This is what is meant by reality being non-local. Reality is non-real. When I discuss this in my courses, I call it as reality 2.0. Our perception of reality is in terms of a clear perception of what is here and what is there. There is no ambiguity about this. But nature has her own way of expressing herself, which defeats this segregation between here and there. That's entanglement. And this entanglement allows entanglement between two quantum bits. And this entanglement is quantum computing. So teleportation and quantum computing becomes possible essentially because of entanglement. So it is an intrinsic property of nature which requires a superposition of states. Yes.
Good morning, sir. Sir, actually I have researched a little bit about quantum computing. Sir, I just wanted to know about qubits and what are the advantages and challenges in future computing that will arise because of this.
Yeah, it's a good question. It has a very big answer. I don't think I can get into too many details, but I did refer to some essential aspects of advantages of using qubits. A qubit is a superposition of 0 and 1. Okay, it is not the way you do classical computing in which you use either a 0 or a 1 and its physical representation. You can do maps and many things with electronic circuits, but it boils down to a switch being either on or off. Okay, in your algorithm there will be no place where you consider the switch to be a superposition of on and off. And that is what a qubit allows. So I explained it earlier by saying that if you want to go from here to Qutub Minar and you don't know at this point if you should go left or right, if somebody could do a calculation for you as to what would happen if you went left and somebody else did the calculation of what would happen if you did right, because you will meet different situations, different traffic jams, different roads, different traffic obstructions, and that will determine your success in getting to your destination. Now, if both of these calculations are available to you instantly at the same time without one after the other, otherwise a classical computer will calculate the probability of success by taking either left or right one at a time. If the switch is either on or off, 1 or 0, one at a time. Whereas a qubit computing, quantum computing, will allow you to get the answer by considering both. Okay, means I don't want to get into the mathematics of vector space, but even with a 7 qubit computing, you can get one state and you want to get to another state. And you can ask how many steps will be needed. And I have these numbers on my laptop somewhere. The details are not very important. But if you use a classical computer, you will need thousands of steps. Literally thousands of steps. Whereas if you use qubit logic, you can get there in 4 steps. Isn't that impressive? And the advantage in cyber security comes from another reason which I have not mentioned. Because of your question, I have an answer to. Suppose you are sending me something, and we are close friends, we are sharing our secrets. Or there is somebody else, he can interrupt the message. Okay? and he can extract that information which you don't want him to know. You want to share it only with me. Apni to yari hai. So somebody else can interrupt and get this message. So the advantage of a qubit is that if you interrupt, that state breaks apart. Qubits are very volatile. So information is very safe. And now with the kind of, I'm sure many of you know how to hack. How many of you know how to hack? Can you hack each other's email accounts? How many of you can do that? Your director is here, she wants to know. Huh? Yeah. All right, but I'm sure that some of you can do that. And I'm absolutely sure that some of them can do that. Yes. But you won't be able to do that if the passwords are secured by quantum bits. There's no way you can do that. There's absolutely no way. It's not a matter of more effort or more time or more computers. You cannot do that. Does it answer your question? Yes.
As you told us, applications like and cybersecurity. Sir, what are the applications if artificial intelligence and quantum computing are brought?
Amazing. Amazing. Very good question.
Fantastic question. Actually, I was going to preempt that question because...
Very good question. I did not have a chance to come to that because the subject is so vast. But thank you for asking. How would artificial intelligence, yeah. So it's a very powerful tool, but the machine has to do some learning. And if this is enabled by qubits, it's of course going to be far more effective. And QML is already a big force. So it's a very important question. Many things are happening in this field. QML logic is certainly being developed. There are many applications. You can do some projects on using quantum machine learning, which is a subset of quantum applications in artificial intelligence. We did a project recently with undergraduate students, so it's something which is very much within your reach. You can do that. Good. Yes.
PhDs in natural language processing, can we integrate this along with NLP, quantum?
I'm sure you can. I'm certainly sure you can. Actually, there is a similar problem that I have been discussing with another friend of mine, which is on music. So in music there are some ragas in which there are similar notes but not the same. So sometimes even if it is the same note, it is not the same usage. The aroha and avroha may be different. So in languages also you have got very interesting and penetrating structures. You need to extract those. You can certainly use quantum machine learning for this. Good. These are the projects you should take up, and they are, I must say, within the reach of undergraduate students. That's the most exciting thing, because people like us cannot immediately contribute to the development of the frontiers, but we can certainly do these problems. Yes.
So I think Dr. Deshmukh ji, I mean, for me, listening to this is, I got goosebumps understanding the nature, the role of nature in this whole science. I mean, we thought it is all about zeros and ones because that's how we have come up. and the relevance in music and the way you explained are fantastic. Thank you. I think it is a brilliant. And in fact, the only question I wanted to ask, I think he's already asked. I mean, because the whole topic revolved around, because there's so much of excitement
absolutely.
on AI, right?
Absolutely.
AI. In fact, last few sessions we all revolved around AI.
Yes, very
And,
true. Absolutely.
Yeah. So maybe I have one observation, sir, because that's the reason I played that video. You must have seen
Yes.
the AWS, that is
Yes.
Amazon's, the cloud services that they offer. So you mentioned during your talk that it's an expensive proposition and quite a difficult thing. So with companies like AWS
Yes.
offering quantum on demand or
Yes,
quantum
yes.
service as a service,
Yeah.
will it be more, I would say, feasible to bring it into VIPS?
It will be feasible, and you were referring to Mighty's program,
Exactly.
and they do offer some access through their programs to institutions. So some of that can be tapped. But I suspect even that will be difficult to access
Okay.
before we can show some work.
Okay.
Because as the ground reality, most of the funding goes to major research players.
True.
Some to the next level and so on. And there are hundreds of universities and even more number of colleges in the system.
Yeah. So,
So-
that's why I said now the private services player
Yes.
like Amazon,
Yes.
AWS. Now, I think the essence of that service is to make it available to everybody, researchers and innovators or whatever.
Yeah.
You think that was the question?
That certainly can be done, but there are easier alternatives.
Okay.
What I would suggest is that tie up with these new companies
Okay.
which are getting into quantum computing. Right in Bangalore, we have a company which is building a 25 qubit computer. And I'll be happy to put you in touch with them.
Sure, sir.
And you can send some students to do internships with them.
Yep.
So it's a small quantum computer. It's a 25 qubit, but not bad. Means you have to get your feet wet. So I think you can certainly take up some projects with them. I'll be happy to put you in touch with them.
No, I think we will build a small closed group,
Yeah.
closed quantum computing interest
Yes,
group.
sure.
Who wants to? I think that's a way to begin. Start small and then enlarge into. But I think apart from the expensive proposition, the difficulty. I was amazed by the one question you answered that on the security aspect,
Yes.
cyber security.
Yes.
I think that makes it for a country like India, which is dependent on
Oh, yes.
American, databases and companies, we can build our own high secure networks.
It is very important because our banking depends on that, our
Correct.
defense strategies.
Aadhaar is also.
Aadhaar, yes, so personal and national security is tied up with that. It's a very crucial thing, and the country has to take up this challenge, and it is these kids who will do that. It's an amazing gathering over here. Thank you all very much.
Any last comments or suggestions you have for the students?
Well, I'll go back to two things.
Sure, sir.
One of which I already mentioned, which is health and fitness. And second is hard work. There is absolutely no substitute to hard work. You have to work very hard. Ask questions. All our learning is in the tradition of the Upanishads, and question answer is an integral part of learning. I must say that this is known to everybody, but in most of the colleges, including the IITs where I have been teaching, students often do not interrupt the teacher.
Yeah.
But, one of the things for which I became quite unpopular among some of my colleagues is I used to tell students that do not rag the new students but do rag your teachers. Ask questions. Okay? Stop them in the class. Interrupt them in the class, find them in the corridor, go to their office and ask questions and demand answers. Don't expect answers because knowledge is vast and the teacher does not have all the answers. So be kind to them.
Sir, I think that
Time. Give them time to get you.
what you said is in this paper as a bold quote. A technology can't succeed if only the people who know how to use it are PhDs.
Yes?
I think it was a fantastic
Absolutely.
conclusion to your
Yes.
talk. Huh? Yes.
Yes. Very true.
Fantastic. So
Absolutely.
this paper, I have a soft copy. I'll give it to Deepali ma'am. So,
Yeah.
sir sent it to me last night. I was just going to sleep, and he said, "Can you get me some 10 printouts?" So I started reading it, and finally I slept at 12 o'clock. So interesting, very crisp, three pages. I am sure this excites you. I mean, it's
Yes.
just a summary of how computing is going to change, and what is it that you can do. So, thank you very much, sir. Thank you.
My pleasure.
Yeah.
Thank you.